Okay, so one thing that percent composition is useful for is finding what is called the empirical formula. So let's do some definitions. The formulas that we write for compounds come in two different varieties. There's the empirical formula, which will always be the lowest whole number ratio, okay? Meaning it's in the simplest form. Like instead of C2H2, it's CH. Whereas molecular formula can sometimes be the true number of atoms in the compound, right? Because sometimes, like, say, glucose, which is a sugar that you're hopefully familiar with, C6H12O6, that has 6 carbons, 12 hydrogens, 6 oxygens in each molecule. But the empirical formula for that would be CH2O, okay? So another example down here, say something is actually C6H6. Its molecular formula is 6 carbons, 6 hydrogens, but the empirical formula would just be CH. Okay? So, some information to keep in mind is that ionic compounds will always be written in empirical formula. Right? There is no molecular formula for an ionic compound. Because you always write the compounds out to the lowest common cancellation of charge. Okay, because sodium and chlorine, +1, -1, you do 1 of each. We don't do 2 of each. All right, magnesium and chlorine can only be written as 1 magnesium, which is 2+, and 2 chlorines, which are -1. All right, so ionic compounds are always an empirical formula. It's covalent compounds that can change as far as empirical to molecular formulas. Okay, so sometimes they may be the same, like in the case of water. There is no way to reduce water into a simpler ratio of hydrogens and oxygens, but glucose definitely has a way to reduce. You can divide everything by 6. Okay, so it depends on the covalent compound whether or not there is a molecular formula that's different from the empirical. So the important thing to get out of this is how to find an empirical formula, either from given masses, given moles, or even a percent composition. Okay, but the steps remain more or less the same. Your first task is to make sure you know the number of moles of each element in the compound. Okay, that may be given to you, or you may be given it in a mass, and in which case you have to use molar mass to convert to moles. But regardless, you have to use moles in order to determine an empirical formula. Right? You can't use mass, you can't use atoms. They have to be converted to moles. Once you have everything set to moles, so say you get 3 moles of carbon and 1.5 moles of hydrogen. Okay? Next step, you are going to take those numbers, and the smallest one, you divide everything by it. Right? So we're going to divide 1.5 by 1.5, which gives you 1, and 3 divided by 1.5, which gives you 2, which means your empirical formula is going to be C2H. Okay? So in this situation, you only need to do steps 2 and 3. Now, sometimes you might get different numbers, like an example we'll see later, where you end up with, 2 and 1.5. Okay? And in that case, we have to use, your formulas can't be written in halves. You can't have half a hydrogen. So then you'd have to multiply everything by 2 or some integer that makes everything whole. Okay? Let's do some examples, and this will make more sense. So, first thing is an example where you are given the mass of each element in a particular compound. All right? So, first step is we have to get to moles. So, for that, you're going to take your 13.5 grams of calcium, set up dimensional analysis to convert that to moles using molar mass, and you get 0.337 moles. And you just continue this for all 3. Okay, so 10.8 grams of oxygen divided by 16 grams of oxygen in the molar mass gives you 0.675 moles. And 0.675 grams of hydrogen divided by your 1.008 grams of hydrogen gives you 0.670 moles. Okay, so this is all step one, get everything to moles. Your next step is to determine which one is your smallest number of moles and then divide everything by it. Okay, so the 0.337 is our smallest number. So if I take all of my mole numbers that I calculated and divide them all by 0.337, I get 0.337 divided by 0.337 is 1, 0.675 divided by that is 2, and 0.670 divided by 0.337 is 1.99, or essentially 2. Okay, so these give you very close to whole numbers, so we're going to use these numbers for our formula. Okay, which means that calcium, there should be 1 of them. Oxygen, there should be 2 of them. And hydrogen, there should be 2 of them. Now, if you gave me this, I would be fine, but a better answer is if you notice OH is hydroxide. The best response here would be CaOH2. Okay? So this is one way you can find empirical formulas, is if you're given the grams. What tends to happen more in reality in science is there's machines called spectrometers that will calculate, you put in an unknown chemical, and it calculates the percentage of each element present, or your percent composition. So if you start from percent composition, the steps stay the same. The only thing is that you have to use those percentages to come up with grams. Okay? So the easiest way to do that is to assume you have a 100-gram sample. Right? Because if you know that 53% of your sample is carbon, well, what's 53% of 100? 53. All right? If you use the hypothetical 100-gram sample, your percentages just become grams. And then from there, you can convert to moles, divide by the smallest number, and if need be, multiply by an integer to gain all whole numbers. So let's see this work. Okay, so adipic acid contains 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen by mass. What is the empirical formula? So if you assume that you have a 100-gram sample, you can assume any size sample you want. Just 100 gram makes the math really easy. These percent signs become grams. All right? So then you just take, like we did before, your grams, divide by molar masses, convert to moles. All right? So carbon, 49.32 grams divided by 12.01 grams in the molar mass, and you get 4.107 moles. Do the same thing with hydrogen, and do the same thing with oxygen. All right? So we get 4.107, 6.8, and 2.70. Our smallest number is the 2.740. All right, so that's the one we're going to divide everything by. All right, and when we do that, we get 4.17 divided by 2.74 gives you 1.499, or about 1.5. 6.8 divided by that gives you 2.48, or about 2.5. And then 2.7 divided by 2.7 gives you 1. Okay? So here we're not getting whole numbers this time. So this time we do have to apply that last step. We need to multiply by a whole number integer to make all those decimals disappear. So since it's 0.5s, the easiest number to use is going to be 2. So if you take 1.5 and multiply by 2, you get 3. 2.5 times 2 is 5. And then just for consistency, we have to multiply everything by 2. 1 times 2 is 2. Here's your empirical formula, C3H5O2. All right? We will be practicing this over the next week, but definitely if this sounds confusing, come in for some help.